Tēnā koutou katoa. In the last lecture, we discussed depth-first traversal, where the grey node that was chosen was always the one that had been grey for the shortest length of time. In this lecture, we'll look at breadth-first search, or BFS, where the rule is that the grey node chosen is always the one that has been grey for the longest length of time. Again, the rule for choosing the next white neighbour is unimportant and will employ the convention that where there is a choice of white nodes, we'll choose the one with the lowest index. In contrast to DFS, BFS takes us away from the root as slowly as possible. We start at the root, visit all its white neighbours, and then the root turns black before we start looking at visiting neighbours of neighbours. So we sweep out the first level, the second level, and so on. Again, the choice of grey node can be made in constant time. So the running time of this algorithm is big theta n plus m, whereas n is the order of the graph, m is the size of the graph. So it's a linear algorithm and the size plus order of the digraph, assuming that, of course, that adjacency lists are used. Let's then look at a quick worked example before we study the pseudocode and look at how we might do some analysis of this algorithm. Okay, let's do a breadth-first traversal of this digraph here, starting at node 0. So we'll start by turning node 0 grey, then we choose the node that's been grey for the longest length of time. There's only one grey node, so it's going to be 0, and then we start searching its out neighbours. We'll grab the one with the lowest index, 1, then we'll go back again, choose the grey node that's been grey the longest, at 0, look for white out neighbours, 2, same again, choose 0 again, 3. Now we've visited all of the white out neighbours of node 0, so we're done with 0, we colour it black, and we choose the next node, which has been grey for the longest length of time, that's 1, and we want to visit its out neighbours. So we'll visit 5 first, back to 1, we'll visit 6, and now we've visited all the white out neighbours of 1, so we'll colour that black. We'll look at 2, we'll see if it's got any white out neighbours. Yes, it has, it's got 1 white out neighbour. Then we'll look at 2, we'll colour that black, we'll colour 3 black. The next one to turn grey was 5, colour 5 black, then 6, and then lastly 4. And that completes our traversal. Let's look at which arcs we used during that traversal by colouring them blue. We used 1, 0, 1, 2, 0, 2, and 0, 3, 1, 5, 1, 6, 2, 4. Notice that all of the nodes in this digraph were reachable from node 0. As usual, if that were not the case, we'd simply get a search forest rather than a single search tree. So what is the protocol we are using to choose our grey nodes in this case? Well, by choosing the one that's been grey the longest, we're using the first in, first out, or FIFO protocol, which is embodied in the QADT. Thus, if we rewrite the general traversal algorithm using a queue for storing the grey nodes, we'll have a breadth-first traversal. So let's look at the pseudocode. Okay, so here's the pseudocode for BFS. As usual, we pass it a digraph G, and here we've got the setup. We set up a queue, which we're going to store our grey nodes in. We set up our colour array and our predecessor array, as usual. In DFS, we set up a seen and a done array. We kept track of times. That's not so useful here. Instead, we keep track of D, which will be the depth of a node in the search tree. And we'll see why as we go on. Okay, so this is just the standard initialization. Then we go through each of the nodes, looking for white ones. When we find a white node, we dive into BFS visit, where all the work will be done. So what happens in BFS visit? So we're given our node S, we'll visit it, so we'll colour it grey. This will be the root node of the tree, so we'll set the depth of that node to be 0, and we'll store the node in our queue. So while we have some grey nodes, while the queue is not empty, then we'll get the thing at the front of the queue, we'll call it the node at the front of the queue, we'll call it U. Then we'll look for any neighbours of U, any out neighbours of U. So for each V which is adjacent to U, so if it's a white node, we'll visit it, we'll colour it grey, we'll record which arc we crossed to get there, so we'll set the predecessor of V to be U, and then we'll set the depth of V in the tree, and the depth of V will just be the depth of U plus 1. Okay, so then we'll store our newly turned grey node V in our queue, and we'll go to the next white out neighbour of U. Once U has no more white out neighbours, we can delete it from the queue and colour it black. At that point, we'll continue choosing the grey nodes that are at the front of the queue until we've got no more grey nodes, everything's turned black. We'll return back to here, we'll check whether we've got actually any white nodes left. If we have, we'll just dive in, we'll create a new search tree over here. Once we're all done with everything in the whole graph is turned black, we'll return to here, and all that remains is to return the predecessor array and the depth array D. Okay, so let's step through BFS for this small digraph. We'll start a traversal from node 0, and so here I've done the setup. All our nodes are coloured white. I've got our depth array and our predecessor array ready to go, and here's our QQ. We've done the setup, we choose node 0, we pass it to BFS visit, and then we're just going to stay in this routine. The first thing that happens to node 0 is that it's coloured grey. We'll set the depth of 0 to be 0, and we'll put 0 in our queue. So now we'll check whether the queue's empty. Of course it's not. So we'll set U to be the thing at the front of the queue, so U is now 0. We'll look for every V out neighbour of U. We've got out neighbours 2 and 4, so we'll start with out neighbour 2. We'll colour 2 grey. We'll set the predecessor of 2 to be U. We'll set the depth of node 2 to be the depth of 0 plus 1. So the depth of 2 is 0 plus 1, which is 1. And we'll put 2 in our queue. Now we're still within this for loop. Now we'll visit 4. We'll turn that grey. We'll set the predecessor to be 1. We'll set the depth to be 0 plus 1. And then we'll put 4 into our queue. Now we're going to come out of this for loop. We've run out of neighbours, out neighbours of 0. So we'll delete 0 from the front of our queue and we'll colour it black. So we're back up to the top of the while loop. We'll look at what's at the front of the queue. So 2, U will now be 2. And look, we've got one out neighbour. We've got 2 out neighbours we can visit. Only one of them is white. So we'll visit 3. We'll colour it grey. Set the predecessor to be 2. And we'll set the depth to be the depth of 2 plus 1. So that is also 2. And we'll insert 3 into our queue. We check this out neighbour of 2, but that's already grey, so we've got nothing more to do with 2. We'll delete it from our queue and we'll colour it black. Okay, so we're at the top of the while loop again. We see what's at the front of the queue. 4's at the front of the queue. It's got no out neighbours at all, so delete it and we'll colour it black. Now we'll check at what's at the front of the queue. 3 is at the front of the queue. It's got 1 out neighbour, which is 1. So we'll visit 1, we'll turn it grey, we'll set the predecessor of 1 to be 3, and we'll set the depth of 1 to be the depth of 3 plus 1, so that's going to be 2 plus 1, which is 3. And we'll put 1 into the queue. All it requires is that we delete these two things from the queue and turn them black. Okay, so we're at this point, we've got an empty queue up here, so we're going to return to the main routine, and we'll return our predecessor array and our depth array. And of course, we should have had null as the predecessor of 0. So let's just have a look at the arc classification in this traversal. We followed the arc from 0 to 2, from 0 to 4, from 2 to 3, and from 3 to 1. So we'll colour those blue as tree arcs. So it might help to draw out the search tree to make it more recognisable as a tree. So it looks like this, and notice that the array D records the level or depth of a node within this tree. So node 0 is at 0, level 0, nodes 2 and 4 are at level 1, node 3 is at level 2, and node 1 is at level 3. Indeed, we'll see shortly that D is also the distance of the node from the root in the original graph. That is the shortest path from 0 to 3, and the digraph, for example, is just D of 3, which is 2, so that's just the level of 3 within the search tree. Let's also look at the other arcs in this digraph and see how they classified after this traversal. Well, 2, 4 is clearly a cross arc, 1, 3 and 1, 0. So 1, 3 and 1, 0 are both going to be back arcs. It turns out that it's no coincidence that we don't see a forward arc here, since forward arcs do not actually occur in BFS traversals. So let's look at some formal results. Okay, here's the result. So we say, suppose we run a BFS on some digraph G, and we look at V, a node in G, and we assume that V is in the search tree with some root R. Then the thing that we recorded in position V of array D, so what we're calling the depth, is just the distance in G from the root to V. How do we prove this? Well, we won't prove this result here, but if you wanted to, you could easily do so by induction. Well, the case where V is the root R is trivial, since dr equals drr equals 0. So this is always going to be 0, and the distance of a node to itself is also 0. The induction assumption is then that the result is true for all nodes U, where the distance from R to U is n, and so the induction assumption is that that's just the depth of U. Then there's a little bit of work to show that if, the distance from V to R is n plus 1, then that's the depth of V in the search tree, so that's dV. And there it's easy enough to show that you get a contradiction if this were not true. You contradict this assumption here. So next, let's see how we can classify arcs using their depth D. It's not nearly as clean a result as we had with the seen and done times in the DFS, but it is still useful. So suppose we're performing breadth first traversal on some digraph G. We've got the arc VW, and suppose we've just chosen the grey node V. Then what can we say? Let's start with the easiest one first. So VW is a tree arc, then the colour of W will be white, and the depth of W will just be the depth of V plus 1. So in other words, we've crossed VW and we set this to be the case. How about with back arcs? Well, if VW is a back arc, then certainly the colour of W will be black when we cross VW, and W is at a depth in the tree which is, well, it's at least one level closer to the root than V. So we're going back up at least one level within the tree. For forward arcs, well, the case is simple. We simply don't see them. For cross arcs, the story is probably the most complex, but let's go through a few cases. So in this situation, the cross arc can either go back up the tree 2 or more levels and bump into a black node there. It can be on the same level and either see a black or a grey node there, or it can be just on the previous level and again see a black or a grey node there. We're not going to give a lot of proof for these, but let's just pick out this one and try and understand why there are no forward arcs in a breadth-first traversal. Okay, so why are there no forward arcs in G after we perform a BFS? Well, let's consider the arc VW in G, and suppose VW is a forward arc. What does that mean? Well, it means that W is a descendant of V in the search tree. Then the depth of W in the tree is at least 2 greater than the depth of V. Since we can't have that dW is equal to dV plus 1, otherwise VW would be a tree arc. Using the result that dW is the distance from the root to W in the graph, so the distance from the root R to W in the digraph is at least the distance from the root to V plus 2. But that leads to a contradiction, since the path that goes from the root to V and then across the edge VW is a path from R to W, which is a length from the distance from the root to V plus 1. So we have a contradiction, as this number is smaller than our supposed minimum, the distance from root to V plus 2. And we have our result. Now, in the case of graphs, the results become a bit simpler. Here we have only 2 kind of edges that can exist after a BFS. Either we have tree edges or cross edges. Indeed, if VW is an edge in a graph, then exactly one of the following holds. So either VW is a tree edge, in which case the levels of W and V will differ exactly by 1, or VW is a cross edge, in which case V and W could either be in the same level in the tree or differ exactly by 1. These results can be derived simply by considering the edges in the graph G as bidirectional arcs and simply applying the previous result that we saw for digraphs. Let's finish this lecture with a look at priority first search, or PFS. Recall that the data structure underlying the choice of grey nodes for DFS was the stack to get the last in first out protocol, whereas the data structure used in BFS was a queue to get the first in first out behaviour. So both of these data structures are just special cases of the priority queue, a more general structure that allows almost arbitrary priority rankings. So PFS is a generalisation of DFS and BFS and allows all sorts of schemes for deciding which grey node to choose next. Now, you've seen priority queues before in this course when discussing searching, but let's quickly review how they work in this context. So each grey node is associated with an integer key. The key represents the priority for the node, where a lower key represents a higher priority. So you can think of the key as representing the amount of time, if you like, a node is willing to wait. A low key means it's impatient and needs to be taken out of the queue quickly. So the rule for choosing the next node is that the node with the lowest key in the priority queue is the one chosen next. In some applications, the key can change throughout time, but we'll restrict ourselves to keys that remain fixed at the value they were given when it was put into the priority queue. Okay, so here's our pseudocode for priority first search. As usual, we've split it up into the main routine and the visit subroutine. So we give it a digraph G, we initialize a priority queue, the array's color and predecessor, we set everything to white, we set the predecessor to be null everywhere, and then we look for white nodes, we dive into PFS visit with the first white node we find, we color it grey, then we'll insert it into the priority queue. And the only difference here is that when we insert it into the queue, we also need to decide what the key is going to be. And so we've got this set key routine, which we don't specify here. It'll depend on the application. And it could be very difficult and very complex, or it could be very straightforward. And then go into this while loop, and we continue until the queue is empty. So we get the node that's at the front of the priority queue. So this peek method will involve searching right through the queue or something like that, but we're not interested in the implementation details. Once again, we visit white neighbors, we turn the first white neighbor, we find gray, and we insert the newly turned gray node into the priority queue, setting its key as we do so, and then we just continue around this loop. Once we've visited a node, all the node's white neighbors, we'll delete it from the priority queue, we'll color it black, and we'll return, continuing until we've used up all of the gray nodes. So while we have the code up here, I want to mention how we can mimic both DFS and BFS using the priority queue. Well, a standard queue, as we use in BFS, has the node that has been in the queue the longest being chosen first. So if we set the key of a node to be the time we first saw that node, that is the time it turned grey, then we'll always choose the oldest grey node. Similarly, to get DFS behaviour, we always want to pick the most recently visited grey node. So that node always needs to have the lowest key. We can get that by setting the key to be the negative of the time we visit the grey node. So for the DFS case, we have set key of V to be minus scene, the scene time of V. So let's do a priority first search of this graph, and we'll use the key of a node to be negative of its index. And so when we put this node into the queue, we'll give it a key of -3. Okay, so I've set up my queue. As usual, we'll start from 0, and where there's a choice of white nodes to visit, remember the priority tells us nothing about which white node to choose, we'll just use our standard convention of choosing the one with the lowest index. So I turn 0 grey, I put it in the queue, and its key is 0. Then I choose its out neighbor with the lowest index, 1. I put that in the queue with a key -1. So now I'm going to choose 1 because that's got the highest priority. I'll visit its white out neighbor 3. I'll pop that in the queue with key -3. So now I'll grab 3 and I'll visit 2. So the priority of 2 is -2. So now I'll visit 3 again because that's still got the highest priority, and it's got an out neighbor 4. This key is -4. Now I'm going to choose 4 because it has the highest priority of -4, and I'll visit 5 from there. So just to show which edges I used, we went from 0 to 1 to 3 to 2 to 4 to 5. And now it's just a matter of choosing 5, then 4, then 3, then 2, then 1, then 0, and they'll turn black in that order. Okay, so you can check that for this example, the traversal we did is not equivalent to either a DFS or a BFS. Okay, how about implementing PFS? Well, its running time will depend on how long it takes to find the highest priority element in the priority queue. For the rules described here, if they were implemented in an array, each key search takes time at least n, so we have big omega n, which means that PFS would have a running time of big theta n squared, which is slower then for BFS or DFS, linear in the size and plus order of the graph. Now, there are more efficient ways of implementing the priority queue ADT than using a standard array, but we don't cover those here.